Chemical reactions can be used to produce electrical energy, and conversely, the electrical energy can be used to carry out chemical reactions that do not proceed spontaneously. So, let us apply some important elementary concepts of standard electrode potential, cell potential, or EM of the cell. Nernst equation gives free energy to solve some questions related to the topic electrochemistry, and today we will be doing NCERT question 3.1 to 3.5. Arrange the following metal in the order in which they display each other from the solution of their salts. 5 metals are given to us and we have to arrange them. As they have given in the order they display each other, and we know that more reactive metal will displace less reactive metal from its salt solution. So out of these 5, most reactive metal is magnesium, which is capable of displacing all rest of the metals given here. Second one is aluminium. After aluminium, next is zinc, which is capable of displacing only iron and copper. Then we have after this iron, and the last metal that we have copper in the end. And all 4 are capable of displacing copper. So the very first metal, the first one, it is having the lowest value of standard electrode potential, and as we move from magnesium to copper, your value of standard electrode potential will increase. And what is standard electrode potential? Standard electrode potential, we know that it is basically the reduction potential. So what we have, tendency for reduction is increasing in this direction. Therefore, tendency for oxidation, we will have this order. And therefore, the one which with the lowest value of your tendency for reduction will be having the highest tendency for oxidation, and that will be therefore the reactive metal. So metallic character will increase in the reverse direction, that is from copper to magnesium. I hope it is clear. Next question given the standard electrode potential value. They have given you 5 standard electrode potential value, and arrange these metals in their increasing order of the reducing power. Increasing order of the reducing power, that means what? We have to always remember that the lower the value of standard electrode potential, that is your reduction potential, higher will be the tendency in that substance to get oxidized, and therefore greater will be the reducing power. So therefore increasing order of reducing power is we will start with the metal which is having the lowest reducing power. So therefore that metal is silver. Okay, and after that next metal is mercury. Then we have the next metal as chromium. Then we have magnesium, and the one which is having the highest reducing power is the potassium. Why we are saying this? So have a look here. They have given the value, and your standard electrode potential value is most negative in case of potassium. Yeah, it is most negative, therefore potassium is here. Then we have the next for less negative value, which is less negative than this, is for magnesium. Therefore we have magnesium here. After this, further lower value which is still negative is for chromium, and therefore we have chromium. After this, the rest of the two values are positive. So lower positive value is for your mercury. Therefore mercury we have in the next position, and for silver it is having the highest positive value for your standard electrode potential, that is reduction potential. Okay, so this is how we are able to find out the answer with respect to the values given. So higher the value of standard electrode potential, higher will be the tendency for reduction, and lower will be the tendency for oxidation, and therefore we give reducing power in this manner. Third question, depict the galvanic cell in the depict the galvanic cell in the reaction. They have given you a reaction, and further you have to answer these three questions. So the first one, we have to show the galvanic cell. So therefore your galvanic cell will be represented as, we will write down the anode on which oxidation is taking place. In this case, anode is this one. Zinc is getting oxidized to Zn2 plus, and anode is that electrode on which oxidation is taking place. So we will write it here. Zinc from solid state is going to the aqueous solution in the form of zinc dye positive ion. Then we have a salt bridge, and after this we will write down the species which is getting reduced. So sorry, this is the species which is getting reduced. So here is the silver. We will write down the cathode on the right hand side. Okay, left hand side will be your anode, and cathode will be on the right hand side. So we will write it here, Ag plus aqueous, that is silver ion from the solution are being reduced to silver metal. So right hand side is cathode and the left hand side is anode. This is how we write the galvanic cell reaction. Next, for the first answer, that is first part given. In the first part they are asking that which of the electrode is negatively charged. So always remember, in this case the electrode on which oxidation is taking place, that is anode. Okay, anode is what, negatively charged, and in our case anode on which oxidation is taking place is the zinc electrode. Okay, next part, the second part. In the second part they are asking the carrier of the current in the cell. Always remember, within the cell the charge carriers are ions. Ions are the charge carrier in the solution, because ions are present in the solution which are charge entities. And outside the solution, that is in the external circuit, electrons are the charge carrier, because they are capable of passing electric current via external circuit. So in the external circuit, charge carriers are electrons, and while in the solution we are having ions. Third part of the same question. Third part is we have to write down the individual reactions at each electrode. So we know that anode is the electrode on which the oxidation process is taking place. So at anode reaction we will write zinc, which is in metallic form, is converting into the ion Zn2 plus aqueous, which are going into the solution by the loss of 2 electron, and cathode is your the electrode on which the reduction process is taking place. So silver ion from the solution are taking electron to give you silver metal at cathode. These are the reactions at anode and at cathode. Next question, 3.4. In this question they have given, calculate the standard Gibbs free energy and equilibrium constant for the reaction and we have to calculate the standard cell potential of the galvanic cell, and the reactions are given. Two reactions are given, and they have also given you the values of standard electrode potential here for each case. Okay, so two reactions are given here, and we will calculate one by one for each reaction. So here I have written for you the very first reaction. In this reaction, your chromium is getting oxidized, while your this is chromium. This is getting oxidized to its respective ions, which are tri-positive ion, while your cadmium is undergoing reduction. Okay, so this is how we show the reaction. This reaction from ions to metal, this is reduction, and therefore it is taking place at cathode, and this reaction is oxidation, that is loss of electron, this is at anode. Now here in this case, one thing you keep in mind, that one metal is here, like for example from chromium atom to chromium ion, tri-positive ions are developed by the what we have, how many electrons are being lost, in this case 3 electron, and since 2 chromium atoms, so we will write here 2 into 3 electron. And in the second case, here we are having di-positive ion, that is di-positive ion is converting into the metal by the gain of 2 electrons, and there are 3 atoms, therefore again we will multiply by 3. So we have to remember here that your loss and gain of electron is always same, that is here in this case 6 electrons for each half cell reaction. Now come to the calculation part. We will calculate the standard cell potential, and which is written as E naught cell, and this is equal to E naught cathode minus E naught anode. Or if we have written equation like this, we can write here E naught for reduction minus E naught for oxidation. Okay, so we will write down the values here. For your cathode or for reduction, the value is minus 0.40 volt. It is this value because reduction is on cadmium electrode. Cathode minus anode. Anode is your chromium one. So here we are writing minus 0.74 volt, and you will be getting value as plus 0.34 volt. This is the value of E cell, and we are calculating this value. Why? Because we will be using this value in the our next calculation, that is for the calculation of Gibbs free energy. Okay, so your standard Gibbs free energy, that is delta R G naught. This is given by the formula minus NF E naught cell. Okay, and what are the values here? N is the number of electrons involved in the balanced equation or the balanced redox reaction. F is the Faraday's constant, and E naught cell we have already calculated here. So therefore we will put down the values. In this case, in our case it is minus N value is 6 multiplied by 96500. Coulombs per mole is the value of Faraday's constant multiplied by the value we have calculated, and answer we will be getting here as 196860 joules per mole, and the answer will be, the value will be negative. And have a look here, your coulombs multiplied by your volt will give you the value joule. Okay, so therefore how we are writing answer in joules per mole. Next we have to find out the next idea, that is your equilibrium constant. So we'll write down the equation for equilibrium constant. It is related with Gibbs free energy by the equation minus 2.303 RT log Kc. where Kc is this Kc is the equilibrium constant, R is the temperature, T is the temperature, R is the gas constant. So we will put down the values and unknown quantity we will calculate. We have already calculated the value of Gibbs free energy, this value. So we will utilize this value in this calculation. It is minus 196860 is equal to minus 2.303. Then we have to multiply it with the value of gas constant, which is 8.314 joules per Kelvin per mole, multiplied by 298 Kelvin temperature log Kc. Okay, this is the calculation, and then we will find out the value of log Kc after simplification as 34.5014, and therefore Kc will be the antilog of this quantity, and it will be 3.172 into 10 raised to the power 32. When we take antilog, like here, this value will become the power of 10, and this we will check the value of this quantity in the log table, and you will get this numerical quantity. So this is our next answer, that is the equilibrium constant value. Now the second part of the same question, here we have again the same idea. Cell reaction is given to us, and in this case first we have to locate the anode and the cathode. Your iron from +2 state, that is ferrous state, is going to ferric state. So therefore this process is from here to here, this is the oxidation, and therefore it is anode. Okay, and the second one, that is second value which is given to us, their silver ion are converting into silver metal. This process is reduction, and therefore this is your cathode. Okay, this is your cathode, and these are the standard values which are already given to us in the question. And first we will calculate the E0 cells, so that we will be able to calculate your Gibbs free energy value, or standard Gibbs free energy value. So here it will be E0 cell, it is E cathode minus E anode. In our case, E cathode is the silver one, so it is plus 0.80 volt cathode, minus anode is plus 0.77 volt. So you will be getting value plus 0.03 volt. This is the answer. E cell is having this value. We will utilize this value in the next calculation, that is your delta G naught, that is Gibbs free energy for the given reaction, that we write it as minus Fe naught cell, and we will put down the value. So number of electrons in this reaction, have a look here, from +2 to +3 state, number of electron involved is 1, and from here +1 to 0 oxidation state, again number of electron involved is 1. So here value of N is 1, okay, because here 1 electron is involved. And next we will multiply with the value of your Faraday's constant, and that is 96500 coulombs per mole, and then we will put down the value we have calculated here. So this is 0.03 volt, and we will be getting answer as minus 2895 joules per mole. Okay, and therefore we will calculate your Kc value also, that is equilibrium constant value also. So delta G naught is given as minus 2.303 RT log of Kc, that is equilibrium constant. So we will put down the values that we have. Delta G naught, that is this value we have calculated. So we will put down this value, that is minus 2895 is equal to minus 2.303 multiplied by 8.314 multiplied by 298 Kelvin temperature multiplied by log Kc. So here we will be getting the value of log Kc After your simplification and calculation, it will be 0.5074, and therefore Kc we will find out by finding the antilog of this quantity. We will take antilog of this, therefore we will be getting value Kc equal to 3.22. so this is our answer. So here we have calculated the equilibrium constant and Gibbs free energy for both the examples. Next question. In the question it is given, write the Nernst equation. We have to write the Nernst equation and EMF of the cell or E cell at 298 Kelvin. 4 examples are given for the combination of cell, and their standard electrode potential values are also given. So we will solve one by one. For each case separately I have written here the equation so that for us it will be easy to find out what we have to calculate. Nernst equation we have to write, and we have to calculate the EMF of the cell at 298 Kelvin. So the first equation, the equation I have written already, and the first we will write down the cell reaction so that we are able to write down your Nernst equation. So cell reaction, what is cell reaction in this case? In this case, your magnesium metal is converting to Mg2 plus ion, in which are going into the solution. This process is your oxidation. Okay, this is your oxidation process. And next part, what is second half cell is in the form of the copper electrode, and we are having copper ion which are already present in solution. They are undergoing reduction to copper metal. So this part is what here, this is your reduction process, and in this process since we are having di-positive ions, so number of electron involved are 2 for this reaction. So for writing the Nernst equation, we should know what is standard cell potential, that is E naught cell we should be able to write. This we will find out with the help of values given to us. So E naught cell is equal to E naught cathode minus E naught anode. Okay, or E naught oxidation minus E naught reduction. So here the values are reduction minus oxidation. So here what we have, reduction value, that is the orange one. This is 0.34 volt plus value. Be very careful for the sign of the values which are given to us, because that will change our answer. Whatever values are given to us, we should write down specific sign so that we are not getting the wrong answer. Sign is very important, which is written before the value. So here the E naught cell we are getting as plus 2.71 volt. Okay, now we will write down the Nernst equation. Nernst equation relate your electrode potentials with the concentration of cell, and here E cell, that is EMF of the cell, is equal to standard cell potential, which we have calculated already, minus 0.0591. This value we are getting by putting the values of different constant quantities, log of substances on the product side divided by substances on the reactant side. Now on the product side we are having magnesium ion and copper metal, and on the reactant side we are having copper ion and magnesium metal. And as far as metals are concerned, pure metals, they have their concentration as unity 1. Therefore we are not writing here in the expression the entities on the product or reactant side for which concentration is taken as 1. Okay, so we'll put down the values here which we have. For E naught cell we have already calculated 2.71. Rest of the value we will write down like this. N, for N value is 2. We have written 2 electrons are involved. and the concentration values are given in the question. So it is log of 0.001 divided by log of 0. We are having 3 zeros in the denominator. So after calculation and simplification, we will be getting value as 2.68 volt after calculation. This is E cell, or this is EMF of the cell. So this is your answer. Next part, the second one. In the second question, we will do the calculation in the same manner. We will write down the equation. So iron is undergoing oxidation to ferrous iron. Yes, and we are having second entity is standard electrode potential, which is cathode. So in this case, we are having hydrogen ion and hydrogen gas on the product side. Okay, and this is aqueous, this is aqueous, and this is solid. And to make a loss and gain of electron equal, or to balance the equation, we'll put 2 here. So number of electron involved in this case are 2. We will calculate in the same manner as we did in the last case. Your standard cell potential will be, for hydrogen electrode, the value of potential cell potential is 0. So 0 minus 0.44 volt will give you a value of plus 0.44 volt. This is the value of your standard cell potential. Now we will write down the Nernst equation. So Nernst equation is written as EMF of the cell, that is E cell, is equal to standard cell potential minus 0.0591 divided by 2 log of entities on the product side. On the product side, we are having ferrous ion, and on the reactant side, we are having H plus ion, but 2 H plus ion, therefore they will be raised to the power 2. We will put down the values here. So it is 0.44 as we calculated minus 0.0591 divided by 2 log of, now we will put down the concentration terms which are given in your question already. So this is 0.001, and in the denominator for hydrogen electrode, the value is written as 1. So therefore, after calculating, we will be getting answer as 0.529, sorry, this is 229 volt. So this is your E cell or EMF of this cell. This is the value. Okay. Next one, for the third part. In the third part, again the same idea. We have to find out what is cathode and what is anode. So here cathode is again standard hydrogen electrode. This is a standard hydrogen electrode, and anode is made up of stannous or tin. So we will write down the cell reaction again in the same manner as we did for previous one. Your tin metal is undergoing oxidation to Sn2 plus ion, stannous ion, which are going in aqueous state, and your H plus ion from the solution are being converted to hydrogen gas. So to balance, we'll put here, therefore number of electrons involved in this case is also 2. So we will write down the value for E naught cell, so that we will utilize in the Nernst equation. It is 0 for standard hydrogen electrode, and 0. This value is given. It is minus 0.14 volt. So this is equal to plus 0.14 volt. Then we will write down the E cell value, that is EMF value. So your EMF or E cell is equal to, according to the Nernst equation, this is equal to what? It will be the first value, E naught cell value, minus 0.0591 divided by number of electrons involved, which is 2 in our case, log of concentration of entities on the product side divided by concentration of entities on the reactant side. Okay, so here in this case, if we see in case of tin, tin is undergoing oxidation. Okay, so this is on product side, and on the reactant side we are having the standard hydrogen electrode. So we will put down the rest of the values and then we will calculate this value, that is E naught cell value we have calculated here. So we will put down this value here and we will get your E naught cell is 0.14 minus 0.0591 divided by 2 log of the concentration. We will put down 0.050, it is given in your question, divided by 0.020. Okay, so after calculating the value, one thing, we are having hydrogen electrode, for balancing 2 ions are taken, therefore we will put 2 here. So we will be getting the value as 0.078 volt. This is the value of your E cell or EMF of the cell for this reaction. Now the last one, that is your fourth one. In this case, first we have to locate anode and cathode. So in our case, your the anode, the one on which oxidation is taking place, is the first one, that is your bromine. So cell reaction, if we want to write here, cell reaction will be your bromide ion are converting to bromine molecule, and since 2 atoms are here, so we'll put down 2 here and aqueous here, plus 2H plus, which is also aqueous, plus H2 on the product side. This is gas and this is liquid. Try to write down the physical state of the entities which we are writing in the reaction. And in this case, since 2 electrons are involved, therefore N, the value of N is 2. How? Because this process, that is your from here to here, this is oxidation. Okay, this is oxidation. And the second one, where we have standard hydrogen electrode, this is the reduction process, and electrons involved are 2 in this case. So we will write down E naught cell value because we will use this in the Nernst equation. This is equal to E naught cathode minus E naught anode. In our case, cathode is standard hydrogen electrode, for which the value of cell electrode potential is 0 minus the second value. Second value is given to us 1.08 and it is positive. So 1.08 volt. So we will get the value as minus 1.08 volt. This is the value for your E naught cell. Now we will write down the Nernst equation. So Nernst equation is written as we will write down EMF first. So your EMF or your E cell is equal to E naught cell minus 0.0591 divided by number of electron involved, which are 2 in our case. Then we will write down the log of entities on the product side. Have a look here. The entities are on the right hand side are these elements. Therefore, for them we will write down the concentration term as 1. And on the reactant side we are having ions. So it is bromide ion. And for balancing we have written 2 before it. So we'll put power 2. Same is the case for H plus ion. Here also we will put down the value power as 2. Be very careful to write down the balanced redox reaction. Now we will calculate the values by putting down the calculated value and the given value. E naught cell we have calculated. It is minus 1.08 volt and minus 0.0591 divided by 2 log of, we will write down the concentration term, 0.01 raised to the power 2 and 0.03 raised to the power 2. And we will simplify this. So this value will be the same, minus 1.08 minus 0.0591 divided by 2, and it will be the log of 1.11 into 10 raised to the power 7. We will find out the log and we will simplify, then we will get value as minus 1.288 volt for the EMF of the cell. This is the value of EMF or the cell potential. Now rest of the values which we have calculated in case of first, second and third case, they were EMF value were coming positive. So those were the spontaneous reaction. But in this case, there will not be any reaction, no reaction. Why? Because this value is negative. So to make this process happen, what we have to do? We have to make this standard electrode potential as the oxidation potential, we have to make it as anode, and this part we have to make at cathode. That is, we have to flip their places, only then the process will be spontaneous. Why? Because here we are getting the negative value. So I hope it is clear. We will continue this chapter electrochemistry in our other your videos. I hope you are able to understand and apply the concept. Thank you. This is all for today.